I am Giuseppe Barca, an assistant professor in high-performance computing at the ANU School of Computing. And today I'm going to discuss a little bit about the challenges, some of the challenges and some of our achievements along the path of enabling exascale quantum chemistry implementations and software. And hopefully by the end of the talk, I will have convinced you that exascale is not pertinent only to users of big computer systems, but it is in general about a paradigm shift in scientific computing that has an impact across the board. The results that you're going to see during this presentation were produced as part of two large international partnerships. One is the Exascale Computing Project, and the other one is the PACER project. They are respectively funded by the US Department of Energy and by the Posey Supercomputing Center. Both of them have the goal of designing an HPC framework for next generation molecular modeling capabilities on computing systems that range from petascale to exascale and beyond. So why are computer systems so important for quantum chemistry calculations? The reason is that the goal of quantum chemistry is to solve the Schrödinger equation. However, this equation cannot be solved analytically. So quantum chemists design methods whose goal is to solve approximately the Schrödinger equation to an accuracy which is acceptable. However, these methods used in quantum chemistry are incredibly computationally demanding. Therefore, it is of crucial importance for the applicability of quantum chemistry methodologies to larger molecular systems or more diverse molecular systems, or for example, simply for faster quantum chemistry calculation for high throughput screening, that the underlying algorithms and implementations of these methods evolve synergistically with the computer systems that they use. So how far did we get with these calculations? At the petascale level, we can do an acceptable job in terms of the level of accuracy of the quantum mechanical model of the systems that we can produce for systems, definitely I would say, with less than 10,000 atoms. If we were able to exploit an exascale machine, we believe that we should get to the point where we are able to model systems with around 100,000 atoms. Now, I use the conditional here because there are two main challenges that need to be overcome along this path of enabling exascale quantum chemistry calculations. The first obstacle, the scalability one, is a well-known one. And so this is about the fact that the amount of computation required to solve the Schrödinger equation scales as a very high power of the number of atoms in the system. And in this table here, there are some of the most commonly used quantum chemistry methods in order to produce predictive models of the quantum electronic structure of molecular systems. We need to be at least at the MP2 level, which scales quintically with the system size. So it's extremely computationally demanding. Another less well-known obstacle is that of the computational efficiency. This is about the fact that many quantum chemistry methods and algorithms today are unable to use efficiently novel massively parallel processors and computer architectures such as the exascale ones. And the main reason for this inability to use these systems is that exascale is enabled by a paradigm shift from latency-oriented architectures, the old good CPUs, to throughput-oriented ones, such as GPUs and other accelerators. For example, the exascale machine frontier draws over 95% of the flop throughput from GPUs. And CPUs are left on the machine basically only for control flow purposes. This means that if you are unable to use the GPUs, an exascale machine is utterly useless. And here in this slide, I would like to discuss briefly some of the challenges associated with these heterogeneous architectures, such as the exascale ones. These are called heterogeneous architectures because they use a mix of different processors, such as CPUs and GPUs in this case. And to illustrate these challenges, I have on the slide here the architecture of a summit node, which is a pre-exascale architecture. You can see already that this is pretty complex architecture. There are 2P9 CPUs on each node of the Summit system and 6 NVIDIA V100 GPUs. Now, by zooming a little bit between the role and interfacing between the GPU and the CPU, what we can see is that the CPU has a much lower flop rate than the GPU, the V100 GPU, about 15 times less. It has also less cores, while the GPU has about 5,000 cores. And then that they have two different memory spaces. And these two memory spaces are able to communicate between each other by moving data through an interconnect, typically an high-performance interconnect such as NVLink. However, this interconnect, if we look at the bandwidth associated with the other memory blocks on the system, is pretty low. So the first challenge is that the transfer between the host and the device is typically a bottleneck because of that low bandwidth. The other challenge that we can immediately see from this picture is that in order to use efficiently the system, we need to expose a massive parallelism because each GPU has 5,000 cores. And also, if we look at the bandwidths, so at the 50 gigabyte bandwidth of the NVLink and the peak flop rate of the GPU, which is 7.8 teraflops, that means that if we want to actually get to the point where we are using those 7.8 teraflops, we need to do much more computation than data transfer, so much more computation per unit of data transferred between the host and the device. On top of that, we need to take into account, for example, that there are 6 GPUs on each node on Summit, and there are 4,608 nodes on the Summit machine. So how do we tackle this scalability and computational efficiency challenge? Well, we need to devise new quantum chemistry methods and algorithms and implementations that have a reduced computational complexity while retaining the required level of accuracy, and that are jointly designed to fully exploit the computational capabilities of throughput-oriented, massively parallel hardware. One successful way to reduce the scaling and at the same time expose more parallelism for quantum chemistry method is to use a fragmentation approach, whereby a big molecule is partitioned in a set of fragments that we call the monomers, and the energy of the system can be accurately approximated using this many-body expansion as a sum of the energies of the monomers plus higher order terms that involve monomer pairs called the dimers, monomer triplets called the trimers, and so on and so forth. Now, there are two main advantages of this methodology. The first one is that this is linear scaling with system size, so we are reducing the scaling. And the other one is that it is an intrinsically massively parallel approach, where we can take all our fragments, so monomers, dimers, trimers, and assign the computation of each of the fragments to a group of nodes. This doesn't really solve the exascale computing problem, though, because we are still left for each of the fragments with the task of efficiently running the underlying energy calculations on a system with potentially many GPUs. In this case, for example, we will have to run the RFFOC and MP2 calculations on systems with potentially even a few tens of GPUs. So we will still need to redesign the underlying quantum chemistry method to run efficiently on many GPU architectures. So along our path to redesign quantum chemistry for the exascale era, we used the Summit system as our test bed. This is not an exascale computer. It's a 150 petaflop machine, which has been the #1 of the top 500 for a few years. But what really is a pre-exascale architecture because it draws all its performance from 27,600 NVIDIA GPUs. And throughout the years, by using fragmentation and redesigning quantum chemistry methods and algorithms for running efficiently on this kind of throughput-oriented architectures, we were able to push the boundary of applicabilities of quantum chemical modeling to larger and larger sizes, record after record. For example, this year in 2022, we were able to perform for the first time an RFFOC plus or MP2 calculation using a fragmentation method known as FMO on a system with over 145,000 atoms. And this was accepted as a publication in the Supercomputing 22 conference. A little bit more about this record calculation. Here on the left-hand side, there is a strong scaling plot of our algorithm. As you can see, we scaled our code on up to the entirety of the Summit system. The percentages there are parallel efficiencies. The largest system that we were able to calculate, to model at a fully quantum mechanical level, was this spherical section of the crystal lattice of this ionic liquid, whose chemical formula is on the first line. This was a system with 146,000 atoms, and we correlated 623,000 electrons at the CCPVDZ. The CCPVDZ arrive-fit basis set levels for the more expert with this staggering number of basis functions. And by using essentially the entirety of the Summit system, the calculation took just about 40 minutes. So what does this slide show? This shows that if we are able to redesign our algorithm for exascale generation architectures, we can actually extend the boundary applicabilities of quantum mechanical modeling, fully quantum mechanical modeling, to systems with around 100,000 atoms. So very different scales. All right, another added value of what we have been doing in this project is that of redesigning the underlying method themselves without using fragmentation, right? So taking the basic quantum chemistry method and redesign the algorithms and the implementation for achieving high performance on many GPU systems. And this slide shows the speed up of our SCF code with respect to the Quick and TerraChem codes for a variety of systems and the basis sets, and using either 1 or 8 GPUs. Here the comparison is a fair comparison. These codes either use 1 GPU and our code uses 1 GPU, or they use 8 GPUs and we use 8 GPUs. So as you can see, we managed to obtain very significant speed ups. These are actually even better now because we've done a bunch of additional optimizations on our code. Another important point is that even by using a single GPU, we obtain the speed up of the order between 20 and 40 times compared to state-of-the-art CPU codes, such as games, but in a fair way. So running in parallel on a single socket with 20 CPU cores, a Cascade Lake CPU. And then also in practical terms, to give you an idea of what we can achieve with this code, we have this RNA-5 example using 61G, 643 atoms, 4,300 basis functions. When we use 8V100 GPUs, we can do 10 SCF iterations in 40 seconds, which means that you can complete an RTFL calculation in probably just below a minute. So this pushes really the timings to different orders in a good way. And same story pretty much for adding the correlation. The MP2 is a method for adding correlation to the systems. This is needed for achieving quantitative modeling of chemical systems, especially, for example, when you do reactions. Here, our baseline is QChem, as you can see in this bar chart, which is arguably the fastest CPU Array MP2 code. And when running QChem on 24 cores of another Cascade Lake, we obtain a speed up, our code is XS, of about 4.2 times over QChem. And this speed up compounds if you look at the strong scalability on the right-hand side when we use multiple GPUs. So 4 by 4 is 16 times. We have orders of magnitude of speed up with respect to the best CPU code out there. This enables us to do these calculations, for example, 45 water molecules with this number of basis functions using 4V100 GPUs in record times, such as this one, like just below 10 seconds. This takes me to my concluding remarks. The exascale era has marked an irreversible paradigm shift in the computational hardware and programming models. This is not something that affects only users of big systems. This affects scientific computing at large and small scales, and in particular, various fields of scientific computing, such as, for example, quantum chemistry, where if we want to enable faster calculations, for example, for high throughput screening, larger systems, more diverse systems, we must redesign the underpinning algorithms and programs to efficiently use exascale generation computational hardware.